All right, let's do section 1.2 now, and hopefully this will go pretty well for us. So first off, we're going to talk about combining functions and shifting and scaling graphs. That's what we're doing here. So the first thing is we're going to look at sums, differences, products, and quotients of functions. So functions, you can add them, you can subtract them, you can multiply them, and you can divide them as long as the denominator is not zero. To form new functions, and that's what we are interested in here. So definition, if f and g are functions, then for every x that belongs to the domains of both f and g, essentially what we're saying is for every x that's an element of the domain of f intersected with the domain of g. In other words, what we're saying here is it has to work in both. So if, say, for example, this is my domain of f, and this over here is my domain of g, then when I add or subtract or do something with them, I'm going to end up getting the domain to be going to be that intersection. It's going to be where those two things overlap, because if it doesn't work in one, say the domain of f excludes anything that's zero because it has to divide by zero or something like that, well then that means when we combine them together, that's still going to be dividing by zero, and so that still has to be kind of excluded. So we're going to ultimately end up with only the things that both of them can handle. If they both can't handle it, then it's not going to be a part of it. So here are what we can do and how we can write this. F plus g of x is f of x plus g of x. F minus g of x is f of x minus g of x, and so on and so forth. So these are just notations here on the left. These parts on the left are just notations to make writing what is on the right-hand side a little simpler. Okay? So make sure you're familiar with those notations because you need to be able to recognize them. Functions can also be multiplied by constants if c is defined, if c is a real number, then cf is defined for all x. Not really enough room there to write that, but there you go. It's defined for all x. So basically we can just go ahead and do that. There's nothing that the constant's going to do to mess anything up. It'll all just work, just multiply everything by that constant and pretty much stay the same. So let's take a look here at an example. And the first thing, it says let f of x equal the square root of x and g of x equal the square root of 1 minus x. So the first thing it asks is, what is the domain of the function f of x? So that's this one right here. And so what is the domain of f of x? And that's going to be pretty straightforward. It's just going to be everything that doesn't make us take the square root of a negative. So we have to exclude all negative numbers because we can't, at this point we're not taking square roots of negative numbers. So we can use 0 on out to infinity. Notice I'm inclusive of 0 because we can't take the square root of 0. Then the next one says, what is the domain of g? Well, we need 1 minus x to be greater than or equal to 0. We can't let it be less than, which means we need x to be less than or equal to 1. And so our domain here means we can go all the way down to negative infinity, and then we can go only up to 1, but including 1, because we have the or equal to sign. All right, so then what is the domain of f plus g of x? Well, this is going to be all the numbers that work for both of them. And if you look, you could even draw this as a number line if you wanted real quick. So here's our number line for f, and it's going to be from 0, right, inclusive of 0, on out to infinity. Okay, so there's our one for f. And then for g, it starts at 1, right, includes 1, and then goes on out to negative infinity. And so when we look at those two, what we're interested in is where do they overlap? And that's going to be right in there. And so our overall domain of f plus g, the things that work for both f and for g, is going to be everything between 0, including 0, because 0 works in both of them, on up to 1, and 1 works in both of them as well. So then the question is, what is f plus g of x? Well, remember, f plus g of x is f of x plus g of x, and so that's simply going to be square root of x plus square root of 1 minus x, and that's pretty much all we can do with that. That's it right there. And that also should fit with our domain if you see it that way, because say, for example, if we try to plug in, -5 or something like that, while that will work over here, it's going to break it here, and so that's excluded. And if we try to plug in something like 10, well, 10 will work here, right? But it will break this over here. It'll give us a negative number. And so the only thing that's going to work is what we found in the domain of f plus g, and that's those values right there. Okay? And now find f times g of x. If we come back to this little table over here, really it's this one right here with a little multiply symbol. Be careful a little bit. We don't want to confuse it with another symbol that we have that we'll see when we do composite functions in a few minutes. But this is f times g of x, so this is f dot g of x, which is going to equal f of x times g of x, which is going to be square root of x times square root of 1 minus x. And since they're both under square roots, we can go ahead and combine them together, and this would be the square root of x times 1 minus x, like that. And that will be our answer right there. Oh, this was our answer up here. Probably little boxes around those, okay? So there you go. Next page here, we have a summary of all the different things we could do to combine these two. There's f plus g, f minus g, g minus f, f times g, f over g, g over f. We don't have g times f because that'd be the same thing as f times g. It doesn't matter which order we multiply them in. And that's also why we don't have g plus f, because f plus g and g plus f equal that, right? So this equals g dot f, and this equals g plus f. So we have all the possible combinations we can do there because those two equal each other. And then take a look at the formulas, and if I were you, I would try to reproduce these just for some practice. Try to reproduce those, make sure you can, and then make sure that you can reproduce these domains, that you understand where these domains come from for them. Okay, and if you have any questions about that, then let me know. The graph of the function f plus g is obtained from the graphs of f and g by adding the corresponding y coordinates f of x and g of x. Kind of squishing that in there, sorry. At each point. So essentially, this is just going through. You see our function here. Here's f of x. It's in blue. Here's g of x in yellow. And what you're doing is you're saying something like, all right, we're going to look at this point right here and say this is 3 high. And then we look at g of x here, and we say, all right, well, at that same point, this is 4 high. Well, then what is f plus g going to be at that point? It's going to be 7, right? We're just adding them up. And you would do that for every point, I kind of didn't pick good numbers because I just noticed I had them there off to the side. But this is 2, this is 3, then this is going to be 2 plus 3, which doesn't, oh, that's not a 2, that's a, yeah, it is. That looks like 2, maybe that one's a 4. Maybe that's a 4. Sorry, I'm just trying to make it fit the picture there. That's a 4, and then 2 plus 4 gives us the 6 up here. That's the 6. Okay, sorry. There's probably a little better numbers than what I was just picking when I... It helps if you actually look at the axes over there. And so basically you can do that anywhere. Say this is a 1, this is a, a 2. Oops, go back. So this might be a 1 here, this is a 2 here, and then that's going to be a 3 there. because you're adding up 1 plus 2 to get the 3. And you can just do that at every single point. This plus this gives you this, right? And so you just add them up. And then you get what the graph of the combined functions is. Okay? So for the next one here, we have a composite functions here, where we're going to actually plug the functions inside of each other. Composite functions definition. If f and g are functions, the composite function is defined by, and we write it this way. This is, again, notation. So don't mistake this notation for f times g of x, right? In the other one, we had f times g. It was just a dot of x, right? That equaled f of x times g of x. This one up here with the open circle is not f times g, it is f of g of x. We're going to plug g of x in for x in f of x. We're going to replace every x with those. So just be certain that you note these two are not the same, okay? Note the difference there, okay? So make sure that you don't do that. If you want to write that off to the side for yourself, I'm not going to leave it in the notes because I don't want to confuse anybody, but make sure you realize that this is not multiply here in this case like it is with the single dot, different from the other picture, all right? The domain of f of g consists of the numbers x in the domain of g, for which g of x lies in the domain of f. Basically what we're saying is you take all the numbers that work for g of x, and then you see what values they give you, and then you see if any of those values would break f of x. So for example, if you were doing something where f of x was 1 over x, and then there was a value that worked in g of x, but it made g of x equal to 0. Say, for example, g of x was 2 minus x. All right, so this is g, this is f, we're saying real quick here. Just a quick little example. Well, if I try to plug in 2 would work in f. I could put in a 2 here. 2 would work. 2 would work right here. 1 over 2 works, and you think, oh, okay, that's okay. And 2 works over here. If I plug in 2 here, I just get 0, and it's fine. However, if I plug in 2, I get a 0 over here. This will give me a 0, and 0 does not work in there. So this is the kind of things you have to pay attention to. You can't just look at it and say, oh, well, here's their two domains. It works for each of them individually, therefore it works for their composite function. That is not the case, so you have to be careful about it. So how do you go about finding, then, the domain of your composite function? So there's a 4-step thing here. I think we can simplify it down to actually just 3 steps here that I like a little better. First step is find the domain of g. That's the internal function, okay? This is for f of g of x. 2, find the domain of f. And then 3, this step's a little bit more writing than the others, but let's see if I can get it in here. Find inputs, basically x values, in the domain of g all right, in the domain of g for which g of x is in the domain of f of x. And that's what I'm saying. If you basically look at your domain of g, and then you have to find what results will that give me. So if my domain of g is 0 to 10 or something like that, and then I have to see, if I plug 0 in, do I get a number that actually is in the domain of f of x? So you not only have to find the domain of g, you then have to plug the domain values in for g, get the results, and then see if those results work in f of x. And basically what we're saying is you're going to exclude inputs x from the domain of g of x, for which g of x is not in the domain of f. All right, whatever is left then is going to be your domain of f of g of x. I hope that made some sense. I know it's kind of tricky, but if you think your way through it, hopefully it'll make a little more sense. It's kind of like saying, you know, I have a machine here, and what I'm doing is, if I'm doing f of g of x, what I'm doing is I'm saying, all right, I have my machine that's g of x, and I'm plugging something into it. And then I'm getting an output, all right? And I want that output. That output is g of x. Well, those g of x are going to get input into f of x, all right? So I plugged in all the stuff that works. So this was the domain of g. This is all the stuff that worked in g. I plugged it in. I figured out all the stuff that's going to come out. And then that stuff that comes out goes into f of x. And this is where you end up getting f of g of x, like that. And so it has to not only work going into g, it has to work going into g, it then has to come out of g, and whatever comes out has to then work in f. All right? That's kind of the best way I can think of to tell you how to work it. It has to work in one, and then it has to work, then the results of it working in the first one, the inner one, have to work in the outer one. Otherwise it won't work. You know, you just have to be careful about that. It is what it is. So think your way through it. If you have trouble with it or anything like that, then just let me know and we'll look through it some more. So let's take a look at the next page here. This is just going through and copying this table and trying some of this, seeing if you can do these. So first off, this is just f of g of x. I'm going to do a couple of these and then not too many. So we're going to plug g inside of x, right? So this will be g inside of x. That means it's going to be square root of x minus 7, because I took the x minus 7 and I plugged it in for x, just like that. Okay, it went in right there. So I'd get x minus 7. And so I'll leave B for you to try. And then look at something like C. I'll do C, and then I'm going to leave the last ones for you to try, and I'll answer them in the notes so that you can see them later. But here this is asking, what would g of x be if we know f of x is square root of x minus 5, and the composition of f of g of x is x squared minus 5. So in other words, what would we have to plug in for x right here, because we're doing g inside of x, to end up with x squared minus 5 there? And the answer is just simply x squared. If we replace x with x squared, we get x squared minus 5 underneath that radical. All right, so again, I'll leave the rest of them for you to try, but in the completed notes online, you should be able to see the final answers. There's the same page just again. And so last here, example 3. For the given function f of g of f of x equals square root of x plus 1 equals, and then g of x equals 1 over x, write a formula for f of g, and then find the domain and range. So f of g of x is just going to be f of g of x. So that means we're going to plug this in everywhere there's an x. So we're going to get square root, and then we're going to put a g of x right where x is, plus 1, just like that. And then this becomes, and that's one way to think of it. The other way I guess you could think of it, it would be to say it's f of 1 over x, like that. Whichever way you prefer, either way is going to give you the same correct answer. And so this will be the square root of 1 over x plus 1. We just plug in g of x right there. And this is the same thing. We're just going to plug g of x into there, and it's, you know, whichever of that second step you prefer, they both give you the same answer. But anyway, I don't probably need to even write that down there. I can just make that a little clearer, so that this will also equal up to there. I don't know if that's clear or not, but they both give you the same thing. So either one of those, either which way you think works better for you, go with it. Now, find the domain. So what is the domain? So first, we need the domain of g. So the domain of g, right? That's going to be, if we look at g of x, that's going to be everything but 0. So that's going to be negative infinity up to 0, but not including in 0, and then a union 0 out to infinity. Not inclusive of anything because you can't include infinities, and 0 doesn't work. Then we need the domain of f, and the domain of f we need to look at is square root of x plus 1. And remember, we need square root, we can't have anything negative, so we need x plus 1 to be greater than or equal to 0, which means x has to be greater than or equal to negative 1. And as long as that is the case, we are good. So this is our domain. We can include negative 1 because negative 1, works. It gives us just 0, and we can take the square root of 0. That's why we have the or equals to sign. And then we've got negative 1 out to infinity, and that's our domain for f. So now we need to see what results from plugging in all these values. Are there any of the values that when we plug them into g of x are gonna give us a number that's gonna be less than negative 1? And so when we do that, domain of f of g, that wasn't very good. That was supposed to be an open circle. Domain of f of g like that. All right, sorry for that little interruption there. But what I'm saying is we need all the values that come from g that are going to give us numbers that are greater than or equal to negative 1. So first off, all the positive values that we plug into g, all the 0 to infinity, they're all going to give us positive numbers, and all the positive numbers are greater than negative 1. So first off, all of that part right there, that's still going to fit. The 0 to infinity part is still going to work because if you plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, any of those, or any decimals or fractions in there, you get a number greater than negative 1. What we have to worry about is on the negative side. On the negative side, we need to know what numbers are going to give us numbers greater than negative 1. Well, any fractions that you plug in, if you plug in something that's between 0 and negative 1, say you plug in, like negative 1/2, what happens is if you plug that in, you get 1 over negative 1/2, which is going to be negative 2. And negative 2 is not greater than negative 1. However, if you plug in something like negative 1, for example, you plug in negative 1, you get 1 over negative 1, that just equals negative 1, and negative 1 is greater than or equal to negative 1. So essentially what we are going to have to throw out here is 1, we can't have 0 because 0 will not make it through g of x. So we have to eliminate 0, and we can start all the way over here at negative infinity because any big negative numbers are going to give us a fraction. So like say you did negative 5 or something like that, you get 1 over negative 5, that's negative 1/5, that's greater than negative 1, and so that works. And so negative infinity all the way up to negative 1 will work, but anything from negative 1 to 0, anything in that little part is not going to work. So we can go up to there, and then we can go anything above 0. Okay, so those are the parts that will work in it, and essentially just kind of think your way through it. But we found the domain of g, we found the domain of f, and we saw which ones of the results of g of x, the domain of those, the results of those were also in the domain of f, and that gave us what we have right there. Okay, that's it on that one. This one I'm going to leave for you to try. This is the other way around. I'll write the answer in the notes, but give you a chance to try that yourself. And so this is not, instead of f of g, it's g of f. So give that one a try and see how it turns out for you. So next is shifting a graph of a function. So vertical shifts. This is going to be when we add an overall number outside of our standard base function, just over to the side. And horizontal shifts are when you add on directly to x inside of the function. So notice that this k will shift up k units, or down k units. If it's a minus, it'll go down. If it's plus, it'll go up, and it does exactly what's there. But over here, this does the opposite for horizontal shifts. A plus h is a shift in the negative direction. It's a leftward shift. A minus h is a right shift. It's going to be in the positive direction. So horizontal shifts, pretty much usually everything that happens horizontally does the opposite of what the sign is, and everything that happens vertical does exactly what the sign is. So just be careful of that. Make sure you pay attention to the sign in which direction it is. So how about this? Write an equation for a function with the given characteristics. The shape of x cubed, but shifted left 5 units. So you should know x cubed shape is like that. So make sure you have that down, that you know these shapes of these basic graphs. It's like that. It's not really needed for solving this, but we want to shift it left 5 units. So shifting it left, that's a horizontal shift. That means we need to do something like this. If we're shifting left, then we want this to be a positive value. So our f of x function will be x plus 5, and then the whole thing cubed. All right, just like that. And this next one, the shape of absolute value of x, which again you should know is that V shape, like this. But shifted down to, so this is a vertical shift, and so we're going to do exactly what is there. So this is a vertical shift. So here, let me underline that. This is shifted down 2 units, so that's this right there. Whereas this one is right 4 units, so again, that's the horizontal shift. I'll do that in red. And so ultimately, what we get is f of x equals, and then we'll have absolute value of x, and then I'll put a minus 4. That's for our shifting to the right. And then we have to have we're shifting down, so minus 2. That's the vertical shift. And so that's what our answer should be for that one. It's going to shift it down and down to right 4. Example 5, the number of units and the directions of the graph of the equation is to be shifted are given. Give an equation for the shifted graph. So we're going to shift it down to left 5. All right. I'm going to let y'all try this one. I just want you to note that this is actually the equation for a circle. And so take that into account when you do this, and that the standard form for a circle, give this one a try. And again, I'll have it done in the notes for you, looks like this. All right, r squared. So try and do this one and see what you come up with for an answer, and then check the notes and see if you got the same thing that I'll put on there for you when I go back and complete it. All right, scaling and reflecting of graphs. Okay, for c greater than 1, you have c times the outside of the function stretches the graph vertically. It's done to the entire f of x, so it's going to work on it vertically. 1 over c compresses the graph right there. So it's doing exactly what it does. If you multiply by a number greater than 1, it's going to make it bigger. If you multiply by a number less than 1, it's going to compress it and squish it down vertically and make it smaller. For here, we've got it multiplying directly on x inside of the base function. And so it's going to do the opposite. Multiplying by c actually is going to compress it horizontally. And dividing by c, or multiplying by 1 over c, which would have been more like the other one, is going to actually make it bigger. It's going to stretch. It does the opposite of what is there. And if c is equal to -1, then we're going to get reflections. So in other words, if we put a negative out in front of the whole entire function, we're going to reflect the graph across the x-axis. That means we are doing a vertical reflection, because this is the x-axis, right? This is the y-axis, and so if we are reflecting across the x-axis, we're reflecting around that way. And so it's like a vertical reflection. Any point that is up here, say there's this point right here, is going to get reflected down to this point down there. Okay, so that's what's happening. It's getting reflected, rotated around the x-axis, and then so reflection across the x-axis is a vertical shift. It's like a vertical reflection, and then reflecting here when you put the negative right on the x is a reflection across the y-axis, where if we do a reflection across the y-axis, here's the y-axis, right? Here's x. That means that any points here, we're getting reflected around the y-axis. So if I have a point over here, it's going to get reflected over to a point over here is what's going to happen. So all the points are going to reflect around that. That's a horizontal reflection, and it does the opposite. So well, not the opposite. It's going to reflect it around that y-axis. That's a horizontal reflection. So, given equation of the stretch compressed graph, I'll do one of these and then let you try the other. So here we have y equals x cubed plus 1, and we want to stretch it vertically by a factor of 2. So stretching vertically is this first case up here, which means we're just going to put it straight out in front of the whole thing. So our function stretched vertically is going to be 2 times x cubed plus 1. Just like that. And then you could even combine it on in there if you wanted to distribute it. 2x cubed plus 2. All right. It is not, all right, this is not 2x cubed plus 1. You have to actually distribute it the whole way through. So don't just put it there. Don't forget your parentheses. Don't forget to distribute. It is not that. All right, I'll let you try the other two there. And again, I'll complete them in the notes for you to look at and check yourself there. All right, example 7. Given the function f of x equals x to the fourth minus 4x cubed plus 10, find formulas to compress the graph horizontally. So we're going to compress horizontally by a factor of 2, followed by a reflection across the y-axis. So a reflection across the y-axis, that is a horizontal reflection, right? We're going to have some point here, it's going to reflect like that. So if this is the point x, y, it's going to become the point negative x, y, wherever it is. So that's our reflection across the y-axis. So first thing we need to do is compress the graph horizontally. So we need to multiply all x's. So this is part A. Multiply all x's by 2, and then we need to reflect across the y-axis, and then we need to make all x's negative. So in other words, what we're doing is f of negative 2x, like that. We're going to replace all the x's with a negative 2x. We're multiplying it by 2, and we're multiplying it by negative 1. So we're getting, so we're getting both of those things all done at once. And so here we go, we can plug it in. We've got negative 2x all to the fourth minus 4 times negative 2x to the third plus 10. And then if we go through and start actually doing this, negative 2 to the fourth power is going to just be a positive 16 x to the fourth. And then negative 2 cubed is actually a positive 8, and then 8 times 4 is 32. I'm sorry, it's not a positive 8, it's a negative 8, but then we have this negative right here, which turns it back into a positive. So we have a positive 32x cubed, and then plus a 10. And that's it. That's it right there. There's our answer. So then I'm going to let you try B. You go ahead and try B, and I'll complete it in the notes so that you can see it at the end. All right, and that's pretty much everything for this section. Thank you.